Okay, so we're going to talk about inverse functions and logarithms all in one fell swoop today. This should be the last lesson of quote-unquote review stuff. Okay, I know you've seen all this stuff, but everybody, well, not everybody, most people did not enjoy logs last year and found them silly, but they are important in calculus. So first things first, we're going to have to understand what one-to-one functions are. You probably know that already, but we're going to talk about it. What's HLT?
Horizontal line test.
Right, we did VLT, vertical line test, HLT, horizontal line test. We're talking about the inverse of a function. We're going to talk about the difference between an inverse of a function and the fact that the inverse of a function is also a function. There's a big stipulation there, and I don't know if you've made that distinction in the past. We're going to talk about the graph of a logarithmic function, which shouldn't be that difficult because we already graphed e, and a logarithmic function looks just like e, it's just raised to a different power. And then we're going to talk about ln, natural log. What's a natural log? No, close. Good, log base e. Log base 10 is just written as log base e is ln, natural log. We're going to change some base forms, and then we're going to work some inverse trig, which you've kind of already done already. I'm going quickly, I apologize, but again, I think this is review, and I want to try to get this done before we leave, even though we still have 30 minutes. If I start going way too fast, just say something and I'll slow down. But otherwise, if I don't hear from you, I'll assume we're doing well. Okay, what does it mean to be one-to-one? This is a new word for me. I've never heard the word injected before. But basically, it means for every x, there's one and only y. There it is in English. You can have a function that's not one-to-one and still be a function, but we're going to be focusing on one-to-one functions as we talk about inverses. By the way, is x squared a one-to-one function?
No,
Why not?
because there's negative x values for one y value.
Very good. That'll come into play later. I like to use the x squared function as an example of when we start dealing with inverse functions. Okay, so there's a lot there. Let me summarize it. First of all is the notation. If we have a function f of x, its inverse is written f to the negative first power of x. That's not a reciprocal function. That's not raised to the negative 1 power. I don't really know why mathematicians started using this, but it's the notation that we use for inverse. Okay, if I meant the reciprocal function of f of x, it would be f of x in parentheses raised to the negative 1 power. Okay, which is ludicrous. Why didn't we just come up with a new notation for inverse? But we didn't, so we have to deal with this. This is a reciprocal function. That's an inverse function. Okay. The other two, number 2 and number 3, are really important, and I don't know if you've seen those before. Did you know that the domain of a function is the range of the inverse, and the range of the inverse is the domain of the function? Let me say that again. The domain of a function is the range of the inverse. And the range of a function is the domain of the inverse. So this opens up a whole new can of worms in that if you have to find the range of a nasty function, and you don't know what the graph looks like, because we talked about the ease of looking at a graph, you can find the inverse and use its domain, because those two things are the same thing. And you've never heard that before?
I wrote that.
Okay. And then how about the last part? If you make a composite function out of a function and its inverse, you get x for both directions. That's also an important thing. Okay. Now, this is where we get into the difference between every function has an inverse. Okay. X squared has an inverse. You could find it, right? Tell me, we'll get to it, but tell me, how do you find the inverse of a function?
Solve for x.
Keep going.
So be the square root of y.
You forgot something.
That's your name.
So, most of you probably learned switch the x's and the y's, solve for y, that's the inverse function, yes? Okay. the function of square root is, it has an inverse. It's plus or minus the square root of x. But that's not a function. Okay, so let me say that again. All functions have inverses. Not all inverses are functions. We're going to focus on inverses that are also functions, and that's what the horizontal line test does for us. Okay, so then switch x and y, like I said, solve for y, and what you get up there is the inverse function. Okay, and then we talked about that guy too. All right, so let's try one. Find the inverse of that function, please. While you're working through that, let's talk a little bit about, well, first of all, does that pass the vertical line test? Yeah, that guy up there. Yeah, it's a function, okay? It's the square root mother function that's been slid to the right 3 and then made a little taller with the 2. Does it pass the horizontal line test? In other words, when I find this inverse function, will that inverse function be a function? The answer is yes. What does this look like? This looks like this. Over 3 goes up a little bit. Okay, so there's that function. That's at 3. Does it pass the horizontal line test? Any horizontal line that I draw through that function is only going to hit in one point. So therefore its inverse is a function. Do you agree, or did I screw up somewhere? I'm good?
No, that's right.
Okay. Oh, by the way, that made me think of something. I noticed a couple quizzes. You never, in this class, have to rationalize a denominator. Okay? So don't bother with it. If you want to, that's okay, but you don't have to. So let's forget about this earlier discussion of inverse functions based on the horizontal line test. Is this a function? Yeah. So we're going to get into this weird explanation of how the vertical line test becomes a horizontal line test when we talk about what does the graph of a function and its inverse have in common. So it looks like this. I have some cubic function, 2x cubed minus 1, and I graphed its inverse also. This can make your life a lot easier, and it's really important further down the line when we're doing more calculus to remember the fact that an inverse, a function and its inverse are reflections of each other over the line y equals x. Okay? So if we go back to, well, let's cheat. We'll use the square root function, or the squared function, and I'm only going to take part of it. You'll see why in a second. Now I bring this line y equals x through here. What's the inverse function of x squared? It's the square root of x. Okay, they are reflections of each other over the x-axis. What happens when you reflect a vertical line over the line y equals x? Somebody's talking, I just can't see who it is.
The vertical line is just going to look horizontal.
Bingo. Yep. A vertical line becomes horizontal. So if we take a function and reflect it over y equals x, we get its inverse. If we take a vertical line from the vertical line test and flip it over the line y equals x, we get a horizontal line. That's where the horizontal line test comes from, by manipulating those vertical lines. Okay. Then the other thing is a little bit of basic algebra. If I reflect the point AB over the line y equals x, it goes to the point BA. Please tell me you know all this. Is that a no? Yes, it's a no?
Yeah,
Yes, it's a no?
it's like, I don't know.
You know? Well, give me some feedback here. Have you seen this before?
Yes.
Yes. Okay. What happened, Fred?
You got it, Brett.
I thought I was just trying to put less.
Maybe you were absent, I think.
Oh, yeah, that, yeah, I remember now.
If you remember the day.
Yeah,
You're good?
yeah, I remember
Okay,
now.
good. We talked about that already. Okay, so that is the horizontal line test, doing whether or not the inverse is a function. Ooh, read number 2. If f is strictly monotonic on its entire domain, then it is 1-to-1 and therefore has an inverse function. Is that even English? Do you know what the word monotonic means? It's simple. It means always increasing or always decreasing. If a function is always going upwards, you're good to go. It's 1-to-1, its inverse is a function, everybody's happy. If it changes from increasing to decreasing, then we got some weirdness going on. Going back to x squared is decreasing and then turns to increasing. That causes problems. I'm sorry, I'm beating a dead horse with the horizontal line test. We did that. Okay, let's go to logs. We're going to go quickly through logs because you don't like them, I don't like them, but we need to talk about them. Graph of a log is the reciprocal, sorry, I didn't mean reciprocal, inverse of an exponential function. Okay, so b to the x would be, its inverse would be the log function base b. By the way, by notation, you know that that is called the base, yes? Okay. The log button on your calculator is actually log base 10. And the natural log button on your calculator is actually log base e, and we said that already. Good. So you can use that to find values. Also, I just had another thing that I need to remind you of. You'll hear me say this a gabillion times. In AP, they want all approximate answers rounded or truncated to 3 decimal places. And I'm going to continue to instill that in you as we go through so you don't make any mistakes. It seems kind of silly. Max solves this big scary problem and he gets 2.4137826. Or 4. Sorry, I have trouble with numbers. But on his answer, he says, oh, that's 2.4. It sucks, but he's not going to get credit for that. He has to have 2.13. Or 2.1414. Truncated, chopped off, rounded. Either answer is okay, but it's got to go to 3 decimal places. Sometimes these things just come to me. Okay, back to log. You did a bunch of work with logs in pre-calculus where you're putting logs together, taking logs apart, all based on those basic log rules. We'll do a little bit more of this in chapter 2, but when you add 2 logs, well, the fancy way to say this is the sum of logs is the log of the product. The difference of logs is the quotient of the values. More importantly right now, let's talk about the change of base form. Let's suppose you want to find, let's suppose you want to find the value of the log base 8 of 5. There is no log base 8 calculate or button on your calculator. How do you do it? You change the you do a change of base problem and write it as, you have two choices actually. You can do log or you can do natural log. I usually, just out of habit, do the natural log. So this would be the natural log of 5 over the natural log of 8, which you can plug into your calculator. You want to use log, you can. You can use any change of base as long as you take that and apply that formula at the bottom. It's the thing you're taking the log of over the base of the log. And then again, this you can easily type into your calculator and take to a number of decimal places. I don't know why I want you to take it to 6 decimal places, but it sounded good at the time. Your friend and mine, inverse trigonometry, going backwards in trig. So we've done, for the most part, we've done problems. Here's the angle, what's the value? Now we go backwards. Here's the value, what's the angle measure? And that can create some problems because you can get all kinds of funky answers. So one of the things that happens early on is we have some domain restrictions, which is what that big scary chart says. Let me summarize it for you. If you're taking an inverse sine function, you're only looking at values in quadrants 1 and 4. One of them has to be positive, one of them has to be negative. Okay, so notice all of those have quadrant 1. That's the value they're going to use for the positive answer. The other quadrants depend on the function as to where you go to get that negative answer. Sine happens in 4, because in quadrant 4 the y value is negative. Cosine happens in quadrant 2. Now, as far as memorizing this or understanding this, I would give you a couple hints here. Remember, 1 must be positive. That's always going to be quadrant 1. So just remember, quadrant 1, the other one must be negative. And you never use quadrant 3. So notice that the sign is negative in quadrant 3 and quadrant 4. Which one is it? It's quadrant 4, because we are never going to use quadrant 3. The other thing to note up there is all of a sudden they start doing this business. So instead of going from 0 to pi over 2 and 3 pi over 2 to 2 pi, they all of a sudden say we're going to go from negative pi over 2 all the way up to pi over 2. So they start introducing negative angles. I don't think that's going to be a major problem for most of you because you understand that negative pi over 2 is the same thing as 3 pi over 2.
What's the I
If and only if. Or it's a misspelling of if. No, I'm kidding. It's if and only if. Okay, so what's the, oh, I forgot to mention this too. I don't know what you did last year, but this is the same thing as that. Have you seen that before? Arc, sine, arc, yes? Oh, good. Okay, some people all of a sudden haven't seen it before, but it means the inverse. Where on the unit circle is the cosine equal to 0? And? In negative pi over 2, very good. Oh wait, why do I only have pi over 2? Why not negative pi over 2? Well, then I have to think about where the cosine is restricted. Cosine is restricted from a positive quadrant, which would be 1, and a negative quadrant, which is 2. Negative pi over 2 is not on that quadrant restriction, so we only use the one answer there. Okay, how about the arctangent of the square root of 3? That is on the unit circle where the y value is the square root of 3 over 2, and the x value is 1/2, and they either both have to be negative, or they both have to be positive. By the way, I'm just giving you what I'm doing in my head. I'm speaking out loud the way I solve the problem. Okay? So this is either going to be the arctangent of the square root of 3 over 2 over 1/2, or the arctangent of negative square root of 3 over 2 over negative 1/2. But I know, because I'm fairly smart, That's not right, because that's in quadrant 3, and quadrant 3 is always forbidden. So we're in quadrant 1. Where is the y value, the square root of 3 over 2, and the x value 1/2? Okay, loud, say proud.
30 degrees,
Also known as?
pi over 6.
It's pi over 3, it's the other one.
Oh, I-
Big Y, small x. What do we got? Last one. Ooh, this one. Not on unit circle. Not on unit circle, 2 choices. Use your calculator, which is what that's designed for, or you have to draw the triangle and solve the triangle using Pythagorean theorem. Okay, so this you would just plug and chug into your calculator. Right now, get out your calculators, please. We're doing okay for time. Hit the mode button on your calculator. Your calculator should always be in radians mode
Oh, no.
in this class. Okay. I don't know if there's another math class or science class that's going to cause you to put it into radians. Like maybe somebody has physics now or something. But for the most part, I think you can put it in radians and leave it in radians for a while.
Physics,
And then, say again, I'm sorry.
physics, just need
That could cause problems.
it's just
I
not-
will continue to remind you to have your calculator in radians, and in fact, that's one of the major things at the beginning of the AP test, is they check to make sure that your calculator is in radians. Because for those of you that have remember doing this with the calculator, when you have it in degrees, you'll get answers, they just won't be right. And we went correct answers. Okay, beautiful. Putting functions and inverse functions together, when you take the sine of an arc sine, for the most part, it undoes itself and you get something simple like 1/2. However, this one, pi over 4 is not in a quadrant that, negative pi over 4 is not in a quadrant that we use for cosine. So this doesn't give us the same answer. I have to take both steps in there. Don't automatically assume that if these two functions are the same, that the answer is going to be that. You got to be careful with that. And then we get to the geometry one. 2/3 is not on the unit circle. So I have to build a triangle, and that triangle looks something like that. How do I know that's the triangle? Because I know that cotangent is adjacent over hypotenuse. Sorry, I lied. Adjacent over opposite. You think a geometry guy would know that. Do some Pythagorean theorem, solve for the hypotenuse. I assume you're all safe doing that. And then once you get that hypotenuse, which by the way, that hypotenuse would be the square root of 13, you can go crazy with all of the other functions, and in this case it's the cosecant, okay, which is hypotenuse over opposite. Okay, almost done. What if it's not a number? What if it's x? Then you just solve it algebraically. You set up your triangle. Now all of a sudden when you solve for that missing leg, you're using Pythagorean theorem and you get something weird like the square root of 1 minus x squared. That's okay. Then you set up your equation by doing the cosine of that and you get that and you're done. We're done. Good, I got it done.